Hello, physics, feedback, and a bit of fun. Teaching with purpose and play. My name is Professor Richard Achaya, and I teach electronics, the module PHYS 2624 at the Qwaqwa campus of the University of the Free State. And that little insert is me recording this video. Hopefully you will enjoy it. So what is my methodology over the years? Following a theoretical class, we have tutorials every so often where students attempt solutions independently, and then we solve circuit currents and voltages together as a class. Next, we carry out an actual demonstration of the circuit with real measurements to show that it's not really just theoretical work, but it is practically realizable. Now, we emphasize the practicality of the circuit with the emphasis being laid on the students, capacitated to carry out these experiments even at home. And because of that, the circuit is built mostly using common parts that either cheaply available or can be scrounged from dead electronics. Now, we do our best to emphasize the importance of graduate attributes. In other words, we emphasize to the student that they should go beyond just getting the degree certificate, but to gain knowledge that will enable them to integrate into society where they can offer meaningful solutions to real problems out there. I hope you will enjoy the video. Thank you very much. We've seen that this current actually happens to have the same magnitude as IE as well, because it's IB plus IC flowing in here. Okay? IB. Okay. So current enters, leaves, we label plus, minus, enters, plus, we leave, it leaves, a minus, plus, minus, it enters here, plus, and minus. So let's try to base enter KB on. The whole point of this one is to find the base current. So we all agree now that it's minus 9, okay, plus 280 ohms. There is 100K. So we can mix and match units. I'm just going to say 28K, and that means that current is going to be in milli, isn't it? K milli will give us volts, okay? And then plus this one, 100K already. IB is definitely going to be in milli, isn't it? It's going to be milli plus VBE. Okay. One of you came to the board yesterday. This is VBE again. So it's going to be, so this is going to be IE. Again, we have 220 ohms, so I'm going to make it K. Remember, K, this is going to be milli, K, milli, and so on. And of course, we're back at the supply. Okay. Yesterday we saw that this is just nothing but how much? Beta plus 1. IB, isn't it? Yes. So to cut to the chase, I'm just going to say these two together will go there. So we'll have beta plus 1. Since I know the beta is 300, so let's just make life easier. So it's going to be 301, okay. 0.28, not forgetting IB, okay, for that, plus, again, 301, 0.22 IB for that, plus 100 IB is equal to the 9 with the 0.7, okay? This here, 0.7. Okay. So it's going to be 8.3 when it goes that side. So collecting terms, we see that IB is just going to be given by 8.3. These two will be 0.5, right? 0.5 times 301 is how much? 1.5, 0.5, right? 150. 0.5, right? Yeah. That's working it out mentally. 150.5 plus 100, right? Which is going to be 250. And remember, we have here we have K with milli. So this currently is going to be in milli. K again. So this is going to be milli. And it's about, mentally again, it's about 0.016, isn't it? How much is this? 8.3? 0.02. No. Is it exactly 2? 3. What else is here? 1. Yes. I did say please don't round up carelessly in electronics. You pay a terrible price. And these 3 significant figures, okay? So the units here will be milli, okay? Because we have kilo, so that must be milli, okay? We have kilo with milli, so that's going to be milliamps. So this is the same as 331 microamps. So it's 331 microamps. So we can then work out what this current is, what I is. It's quicker to work it out. So IE is just beta plus 1 times that, beta plus 1, okay? IB, so as before, we're just going to say 301 multiplied by this. So it's easier to keep this unit, 331. This is about a third of that, okay? So it's about 10, isn't it? 301 times 0.0331. It is? Yes, it's about 10. So it's milliamps. So it is 9.96 milliamps. Okay? Okay. So immediately we can work out what VE is. You'll see that VE is just that current multiplied by that resistance, isn't it? So it's going to be this current, 9.96 milli. That means this has to be in K, isn't it? It's 2 points, right? 2.19 volts. 2.19 volts, right? 9 volts. Okay. So we know that this is 2.19 volts here. Okay. What about VC? VC, of course, is just the number of oranges here, take away the oranges being eaten here. This voltage is, but the quicker one is to simply say 9 minus IE times RC. So since we're putting this in milli, that has to be converted to kilo. So it's going to be 0.28. So it's 9 minus IE, which is this one, 9.96 multiplied by 0.28. How much is that? How much? 6.21 volts. Okay. So this voltage here, 6.21. Okay. And what about VB? VB is straightforward because going from here to here, you're losing 0.7 to get VE. Okay. That means this voltage must be VE plus 0.7. So VB is just VE plus VBE. So how much is that? VE was 2.19, so this is 2.89 volts. So here we're expecting plus 2.89 volts. I'm putting them in square brackets because those are voltages that I can actually measure externally. Okay. So virtually everything is solved. I mean, we know IB gives you, the correct results. Even if you see that I needed to find IE before I could find VB. Can you see? Yeah. So it doesn't matter. I really don't worry about that. Okay. So that's the essence of it. But now, the whole point of having our demonstration Friday, like I did say, some of the Fridays I really want to have as demonstration Fridays, is that you get to see that it's not just a theoretical thing, okay? And now would be a great time for you to just please come without crowding me as much as, like, come very close. I built this circuit for you using exactly those components, okay? Just come up here. Transistor is this black thing here. I'm sure you've seen things that look like that. Not everything that looks like that is a transistor. Okay. You want to show us transistor? They're very nice. This is an oscilloscope, by the way. I mentioned it in class. Well, not in class, but in the practicals. Digital storage electronics, 200 megahertz. It's really a fast one. 4 channels with other controls, digital storage and everything. Okay. So,
does it work as the same as the one we use on practical?
The principle is the same, measures voltage and time, but it has all the bells and whistles of a modern electronics laboratory. Okay. Or instrument that you'd find in modern electronics. So this is the circuit. What I want us to do here is just to, for now, ignore everything else, okay? And just concentrate on the circuit. This I think you've all used this before, right? This is just a digital multimeter. So I'm going to turn this on. It's powered already. There are 2 power supplies here for a reason, okay? Although the 9 volts is just coming to the transistor, so don't mind the other one for now. So there's the 9 volts. I can set it to precisely whatever I want. The circuit is already drawing 9 milliamps for some reason. Okay? I think some of you might actually guess why this is the 9. You see? Okay? The 9 milliamps are being supplied from the source. You see? So what I'm going to do here is I'm going to measure, first of all, VBE. What value do we expect for VBE? 0.7. So from the base, which is the middle pin in this particular transistor, to the emitter, let me just make it nice, to the emitter, which is this one here, to its emitter. Sorry, don't mind this. What are we getting? 0.712. So is this correct?
Yes.
Yes. Okay. Let us measure VE. Let's measure VE. Okay. VE would be across the emitter resistor. What value are we expecting there? 2.19. Let's see what we are measuring. We're getting 2.04. Is that reasonable?
Yes.
Okay. What about VB? 2.89. The base to the ground, okay? 2.74. Can you see?
Yes.
Is that reasonable?
Yes.
What about at the collector? 6.21. At the collector, which is this point here, 6.35. Is that correct?
Yes.
Yes. What is VCE from the collector to the emitter? It's going to be 6.89 minus 2.19, isn't it? From the collector to the emitter.
Yes.
Okay, how much is that? 6.21 rather, minus, it's about 4.0, isn't it? 4.02, can you see? 6.21 minus 2. From the collector to the emitter, what are we getting? 4.3. So this transistor is sitting more or less. Why are there differences? Because even if I've said the beta is 300, chances are the beta is slightly out of that range. Okay? It could be slightly lower. Could be actually slightly higher, to be honest with you. Is that clear?
Yes.
Yeah. Now this, I didn't really need to bring this, I just wanted to show you something. But the whole point of this is that this is actually an amplifier, okay, that takes a real input through this DC blocking capacitor, this one here. This is the input capacitors, that's the output capacitance. And you will see that I've loaded it with 1K for now. From that to the ground, there's a 1K resistor. Can you see that resistor?
Yes.
Okay. That, this one. So we're looking at one of the channels, this one, the yellow one. Okay, it's at a very high gain right now. Let me reduce that. And if I touch that, you see what happens? This is basically the noise signal coming from the mains. My board is picking it up. We all pick up that. Okay. If you touch the inputs of an amplifier, some of you who are DJs and you know what you hear in the speakers, buzzing noise, right? That buzzing is actually from the mains that your body is picking up. It's always present around. So if you measure that frequency, you should find that it's actually 50 hertz. Okay? You can see more or less, because of the other noises, this is playing that. Okay? So right now, there's nothing in the input, so that line is just showing that. But if I touch the input, which is this wire here, you can see the amplitude is actually much, much higher. It is significantly higher, but it's really noise right now. Okay, I'm not interested in that so much. So this circuit here has the correct bias current. It's just waiting for an input signal. That's all. So what I decided to do was to bring in my class D power amplifier that can deliver up to 10 watts of power. Believe it. Switch mode power amplifier, which is going to take this tiny input, okay, and do something with it and drive hopefully a speaker. So I'm taking the output of that circuit from that capacitor, between the capacitor and the 1K, as you can see, connecting it to this class D. This is external, okay? And basically having and by the way, that's now why we get a separate power supply. It's only being driven by a 5-volt supply, this 5 volt, okay? This module here, okay? So we're done with the meter. So now I'm going to turn this one on, but I'll do something else. Now there is an additional real input which is coming from here. Have you seen this little thing before?
Yes.
Where? From where have you seen this? From phone. Yes. I've actually taken this from an old phone, a dead phone. Okay, I showed it to Tanika over there. And I soldered it onto Verboard like this, just to give it a form. Okay? And I've stuck it down with double-sided tape and biased it because it needs to be biased. There's a field effect transistor in here, okay? That you need to supply with power before it will do what it's supposed to do. So this 10K resistor is just to bias that condenser microphone, okay? So now, when I turn this on, and put this here. Come over here. Come on. The ladies are pointing. I don't know why.
1, 2, 1, 2. I can't sing.
Let me sing for you.
Okay. Go on. No, leave it. It's recording.
No, I want to show us.
No, leave it. So, yeah, you can say whatever you want to say. You can talk, you can.
Yeah,
Yeah. So let me show you. The reason it's actually howling like that is positive feedback. Okay. You remember when we talked about body temperature the last time? I talked about negative feedback, where when there's a tendency for your body temperature to rise, the internal mechanisms of your body, your biological mechanisms, kick in to try to bring that temperature down. Okay? For instance, you sweat, you shiver, and all these are changes that are designed by nature to restore your normal body temperature. Positive feedback, on the other hand, means that usually an amplifier picks up some kind of signal, in this case a sound signal, amplifies it, sends it to an actuating device, in this case a speaker, right? And the sound is reproduced in the speaker. But now what happens is that the sound is loud enough to be picked up here now. And the whole process now repeats at a very high frequency. And that frequency is characteristic of the loop conditions. In other words, the optimal rate at which that energy can be exchanged for that particular circuit is resonance, okay? Meaning that it no longer needs an input. Just an initial disturbance, which quickly causes sound to be played here. That sound is loud enough to be picked up by the microphone, and it establishes a loop. Okay, so that's oscillation. And you can just find out the optimal here. Okay, there are many ways of doing it, but we can just find out on the oscilloscope what that frequency is of that loop. I put this here, okay, and then circuit between the input and the output optimally at 600 hertz. Okay? It no longer needs additional input. And the way to stop it from howling is to disturb that loop, to break the exchange of energy within that loop. So there's any number of ways of doing it. For instance, you can reduce the volume. I could have put a volume control here. Before it goes into the amplifier, just reduce that volume. Or I position them differently such that, you know, the microphone no longer picks up what the speaker is doing. And I also built an AM detector. An AM detector, radio signal detector, which I showed her. It's just that I did not want to bring all these things here. And instead of using the microphone as the input, I can connect the output of that dye detector here, and immediately you will actually hear the hiss that we associate with AM radio, like that. And when you tune it under the right conditions, you should be able to pick up a radio signal, a radio station broadcasting in AM, like play through this very speaker. Okay, so this is not just a textbook or theoretical thing. There it is in front of you. Okay, and another thing, by the way, I did say to you, if you remove that capacitor there, the 47 microfarad, which is this one, you reduce the gain. You can just demonstrate. I just pulled it out. It's no longer doing what it's supposed to. It is still there, but at a much, much reduced gain. So by putting this back, I'm providing a path to AC signals. The AC signals from my voice alternating, very tiny, you know, will now have a path to ground in the emitter, okay? Which is just basically connecting it to the emitter. And the gain is back, okay? Very practical circuit. And what stops you guys from making amplifiers? By the way, who plays guitar? Anyone play guitar? Okay. If you have a guitar, even an acoustic one, you can make an electromagnetic pickup like this. It could even be a microphone that will enable you to amplify your guitar sounds into a much bigger amplifier. It's money sitting here. You could specialize in just audio. Building such circuits will have practical applications. It could be a baby room monitor. Connect this to a baby's room. When the baby cries, you can do all kinds of things with this sound. Okay? It could even be used to burn people, and I would not recommend that you do this. Okay?
So you said bugging.
Yes.
How do you do that?
No, for me, I'm just showing you this from the educational perspective. What you do with it is something. Information is power, basically. So if you have it, you're a powerful person. The point is that this is not just theoretical. This is real practical knowledge, real applications. And where the applications, there are solutions waiting to be offered by you. I hope you understand that. So take these things very, very seriously, okay? Any questions? I think we will end the questions. I really appreciate asking. But tackle these things from a very different perspective now, because one of the things you're supposed to do, by the way, as graduate students, I mean, when you graduate, is to have demonstrable graduate attributes. In other words, are you just waving a piece of paper saying you have a degree? Or can you actually fit into society and offer solutions? Those are very important attributes. Because then again, there will come a day when I have to compare one candidate with another, and they're both waving that small piece of paper around. And who do I take? I'll clearly go for the one that can offer something that I'm actually taking. You understand? And those are the graduate attributes we're talking about. It has to go beyond just a piece of paper that you call a degree. Okay? Yeah. I'm dedicated enough to spend the afternoon yesterday, busy as I am, building this certificate. Now, some of you might say, but I don't have a breakboard, I don't have this, I don't have this. I was debating with myself, growing up doing the electronics, I was saying, but I don't have these either. I don't have fancy things. So power supplies I built. Obviously, no oscilloscope, so that didn't matter too much. Because it was only on a wish list, okay? So what do you use for the substrate? Can you just give me that book? I built a lot of circuits on this. And how do you do that? You simply cut it. And then with a needle, you make holes, transistors you see thin. And with the strand, one of the fine strands of needles, simply wrap on the pin. And the circuit worked. It didn't care that it was built on something like this. Through that, you learn a lot. Nobody gives you that knowledge that you have acquired in the world. So don't make excuses. I can't do this because I don't have this. I know you've got challenges, but human beings are unique in that when you have challenges, that's when we kick into high gear and like, not a problem, I will deal with it. But if you're already defeated before you started, I don't know what else to say. Change that mindset. Okay. Very, very important to see it and say, you know what? Certainly, by the way, you have access to the knowledge. I'm there. Others are there. Tandika is not designated for this lab, but she volunteers all the time. So does my daughter. You see, and that shows me a lot that they are going beyond their call of duty. They've got things to do, that's what the graduates. But they're dedicated to you. So I think you have access to the right knowledge.